How about it? You just say.
Why don't we just start? Okay, you all know Eric. His paper, Schematizing the Observer in Physical Theory.
It's not showing up.
Oh, it's cool now.
Oh, that's fine. It's not showing up.
And we all want to wish him happy birthday right now.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Eric. Happy birthday to you.
All right.
Well, I actually want to thank y'all, both the speakers and the audience, for what has been an incredibly wonderful birthday present. Today has been fantastic. So I hope I can keep up minimally to the level of the talks and discussions so far. I want to thank the organizers of the conference for the invitation. Also, it's a great honor. I was surprised to get the invitation. I also want to thank JB because for the best strategy ever for answering Q&A, dealing with Q&A. So for all Q&A, I'm going to make you all answer your own questions. Heads up right now. Also, I want to. I guess I'll begin by saying that I mentioned this morning that I've spent 20 years trying to prove Howard wrong, and have never done it. I don't think I'm going to do that in this talk either. The talk is very strongly inspired by and based on the paper, some reflections on the structure of our knowledge in physics that Chris Mink talked about earlier. But I actually suspect. So while I say I'm not going to argue that Howard is wrong in any sense, I'm extending it in ways I actually kind of suspect Howard wouldn't like and won't like at all. But that's not the same thing as proving it wrong. Let's see. So, and I also just say one last thing by way of preparatory remark, which is that even though I've sat in numerous lectures and seminars with Howard, I only ever saw him give 2 talks, and both times he read the talk. So I'm actually going to, partly in honor of him, I'm going to try and do that as well. Well, I'm going to do that as well. Y'all who know me have seen me give talks know that I normally just kind of wildly extemporize in some hysterical fashion. But I'm going to try to read and see how that goes. So I suggest that the principal difficulty is not that of how to leave the theory outside the laboratory door, but that of how to get the laboratory inside the theory. Well, how do we do it? For of course we do put theory and experiment in relation to one another. Otherwise it would be impossible to test theories and impossible to apply them. It would also, I should add, be impossible to understand a theory as anything but a purely mathematical structure. Impossible, that is, to understand a theory as a theory of physics, if we had no systematic way to put the theory into connection with observation or experience. I also just want to remark that I'm really grateful to Smink for having introduced some of the themes I'll be focusing on today, and in particular the paper of Howard's I'm most inspired by. And as Smink did it in this characteristically elegant, equable, measured, restrained way. You know what I'm thinking of, the Gordon Fest script. So I'll pick up these themes in my characteristic, frowsy, frenetic, unrestrained, and mildly hysterical way, even though I'm going to be reading. What a theory is. And you may wonder why I'm beginning with this question, but I hope it will become clear. What is the theory of general relativity? Now here's one way to make that question somewhat more precise. What is the more or less secure fund of scientific knowledge that constitutes the theoretical and experimental content of the theory? This formulation of the question is certainly not a standard one in philosophy of science. On that standard view, the emphasis is almost invariably on constructing formal models corresponding to something like solutions to the field equations, or equations of version of the theory, and perhaps asking when 2 such families of models or other formal structure are isomorphic in a supposedly relevant, physically relevant sense, with perhaps a vague gesture at the possible representational capacities of the formalism as an afterthought. And yes, that's directed at you, Jim. So I do not like a formulation of the question that admits as an appropriate answer such a purely formal structure, along with perhaps the fixing of something like a Tarskian semantics or a sketch of representational capacities. A formulation of that kind assumes, with no argument ever given, I've never seen an argument for this, that it is possible to make a clean separation between, on the one hand, one part of the scientific knowledge that, say, general relativity embodies, namely that encoded in the pure formalism, and perhaps some interpretive principles attached to it, and on the other, the remainder of the knowledge that general relativity embodies. And the remainder of that theory's knowledge, the knowledge content of the theory, includes, in a minimum, what is encoded in the practice of modeling particular systems, of performing experiments, of bringing the results of theory and experiment into mutually fruitful contact, including, in particular, all the inexact mathematical techniques that cannot be formalized, approximative and heuristic techniques motivated by loose physical arguments and principles that are not part of the formalism or of interpretive principles, and they're justified only by their practical success. So the remainder of the theory's knowledge includes, in a word, real application of the theory in actual scientific practice. So this assumption that these two parts of the theory, the knowledge content of the theory, so to speak, are cleanly separable, comes out most clearly in the picture of semantics that naturally and standardly accompanies the standard view of theories. Semantics is fixed by ontology, and all epistemology and methodology and other practical issues and considerations are segregated in the theory's pragmatics. Again, I don't think we should assume such a clean separation is possible without an argument. If one accepts my formulation of the question as fruitful and interesting, then I think it becomes plausible that the theory of general relativity does not, and indeed cannot, in any interesting sense, consist of the theory of Lorentzian form manifolds, along with a few interpretive postulates or a family of Tarskian models or a class of possible worlds or anything along those lines. Now, it may turn out that I'm wrong, and that a compelling analysis attempting to answer my formulation will show that, in the end, in fact, the standard assumption of a clean separation of the relevant domains of knowledge, the theoretical and the practical, for lack of better terms, is a good and justified one. I personally doubt it. So I will argue in this talk, in this paper, that the interplay between theory and practice, experimentation, observation, modeling, heuristic and approximative forms of argument, is far more subtle, nuanced, complex, and rich than philosophers tend to appreciate, or at least tend to discuss, or to perhaps tend to remember when discussing such things. I think we all kind of know it. We just sometimes, I think, forget it in our discussions. The sum scientific knowledge constituted by the theoretical and practical content of the theory, which for the lack of a better term I'll call the epistemic content, essentially includes knowledge we have gained, and more importantly could have gained, only through practical modeling, experimentation and observation, heuristic and approximative techniques of argument, and in particular, the application, as I'll further argue, of representations and models of such experiments and observations in our theory by the use of these heuristic and approximative techniques of argument that cannot be represented in the formalism of the theory in any rigorous or precise way, and in fact are often, strictly speaking, inconsistent with the formalism of the theory. This epistemic content, this sum of knowledge that a theory embodies and that I claim is perhaps the most fruitful and useful way of thinking about the theory itself, cannot be cleanly separated into a formal and practical part. That's what I will be attempting to argue for. And this is, if I'm right, this is why I think my formulation of the question based on the idea of knowledge is a fruitful sharpening and refinement of the question, what is a theory? For it is exactly this epistemic content in the complete sum that I've just kind of have been sketching or gesturing at that distinguishes general relativity as a physical theory as opposed to a merely mathematical structure. I will further argue that a crucial component of that content consists in knowing how to, in Stein's phrase, schematize the observer. And I hope I'm going to address some of Michael's worries that came up in the question and answer period during Kareem's talk. So how to schematize the observer in theoretical representations of experiments. And this, I've completely lost my train of thought. I've changed time zones too often in the past 2 weeks. I will further argue that a crucial component of that content consists in knowing how to, in Stein's phrase, schematize the observer in theoretical representations of experiments, and cannot be had without models of experiments in which the observer is schematized. Well, and this is by way of trying to, in fact, perhaps not so much address a short circuit Michael's concerns. By schematize the observer, I mean, I think if you press Howard on it, he would probably say this as well, although that's actually not quite clear to me, because he does talk about situating us as observers within the complete pattern of experience in a kind of Kantian sense. So actually, no, I take it back. I'm actually not sure that Howard would agree with this here. But for my purposes, I actually do want to say it suffices for me, and I think it suffices for my purposes to mean only, by schematize the observer, only something like, in a model of an experiment, to provide a representation of something like a measuring apparatus, even if only of the simplest and most abstract form, such as a line of sight in astronomy, that allows us to interpret the model as a model of an experiment or an observation. Such schematic representation, moreover, is not possible, I claim, in a physically significant and cognitively substantive sense, without recourse to all the other components of what I'm calling the practical part of scientific knowledge. This, I claim, is what is needed in practice, the ability, not to schematize the observer, not necessarily that one must do it every single time one thinks about how theory hooks up with the world, but just that in principle we have to know how to do it when push comes to shove and we're really called upon to do it. This is what is needed in practice to bring theory and experiment into fruitful contact with each other, most importantly in the way that warrants our belief that the formal part of the theory is about the physical world, that we're dealing with a physical theory and not just mathematics. I don't think interpretive principles and sketches of representational capacities on their own, so I don't think they can do this. They themselves must be justified first. We must know when someone says, null geodesics on a Lorentzian form manifold are the possible paths of light rays in vacuo, and that's part of my physical interpretation of general relativity. Oh well, that's fine so far as it goes, but I want to know what warrant we have for believing that. And if you look solely at the formalism of the theory and solely at the interpretive principle, nothing in that nexus can possibly tell us why that's right. But if we can't say why that's right, then I don't know why I should believe that that's right and that null geodesics on a Lorentzian form manifold represent really something about the physical world, viz. Possible paths of light rays. Because the meaning of scientific terms and propositions must rest on the knowledge we have of the physical world, and most of all on the knowledge we have gained through controlled observation and measurement, that is, through experiment, epistemic content accrues to a scientific theory in no small measure through the successful construction of representations of physical systems in the theory's terms. At bottom, then, what secure epistemic content a scientific theory has must rest on the meanings expressed in a sound articulation of experimental knowledge. This requires, in a minimum, that we be able, at least in principle, to construct appropriate representations of actual experiments and observations in the frameworks of our best scientific theories. That is, representations of physical systems and experimental apparatus in relation to each other as required by particular actual experiments, not just representations of physical systems implicator in abstraction from actual experiments. I mean, this idea is perhaps most prominently championed by von Frosten and his followers, that in order to understand the physical content of a theory, we do not need to be able to model experiments, simply the physical systems themselves. I just completely disagree, as you probably have figured out by now. And I'll try to give you some actual reasons why I disagree. It is characteristic of the ways that such models are constructed and applied, models of actual experiments, models of physical systems and experimental apparatus in relation to each other in such a way that we can say this is a model of an experiment, and not just a model of a physical system going about its merry way. It's characteristic of the way that such models are constructed and applied, moreover, that they require methods and warrant forms and aspects of knowledge that go far beyond what can plausibly be claimed to reside in the formally theoretical sphere of a theory, no matter how many representational capacities one ascribes to it or interpretive principles one affixes to it, for the reasons that I was suggesting before. These representational capacities and interpretive principles themselves must be justified. We must understand why we have the warrant for believing them in the first place. They can't give us the warrant for the physical content of the theory. They perhaps fix part of the physical content of the theory, but I want to know what the warrant is itself for believing that these principles are the part of the correct story of why this formalism is about the world in the way that it is. As probably most, if not all of you know, a very great philosopher of science passed away very recently, but Bill Demopoulos. And he has a very beautiful line in a manuscript that he left somewhat unfinished, but that I hope will get edited and completed. It's a beautiful piece of work on theories. He says that, let me make sure I'm not going to misquote him here. An accounting of the empirical knowledge that a theory gives to us is incomplete if that accounting cannot tell us why we should believe the empirical content of the theories that we attribute to the theory. I completely agree with that. So interpretive principles of the sort envisaged by the standard view can at most fix only a relation of descriptive representation. What is primarily at issue here, though, however, I'm claiming, more than arguing, I suppose, however, it's not the relation of representation itself, which can at most tell us what the world would be like if the theory were true or largely true of it, but rather the understanding and comprehension the theory gives us of the world, insofar as we are warranted in thinking of those models as representations, which goes far beyond a description of how the world would be under those conditions, the condition that the theory is true or largely true, or extremely approximately true, or something like that of the world. And perhaps I should say that my picture of my use of the word knowledge so far, I haven't said anything about it at all. I should perhaps say right now that by knowledge I don't mean propositional content of indicative sentence, truth value, maybe including substantive conditionals, just descriptions of states of the world and possibly gnomic structure of the world. I mean something in much more in the pre-Cartesian tradition, before we all became so neurotically worried about and neurotically obsessed with certainty. I mean something like understanding and comprehension, the kind of thing that that Wigner, I take it, was pointing to when he said we use quantum mechanics to calculate the density of lead or aluminum, and not just to compute probabilities of scattering amplitudes. Quantum mechanics tells us about the world. It tells us why things are solid. It tells us why fluids are viscous. And it's very difficult to articulate the understanding of the world we gain from these theories if one restricts oneself to and sticks only to the formalism and a few interpretive principles. And so this can be seen clearly in the fact that, what can be seen clearly in the fact? That the interpretive principles I'm talking about can at most fix a relation of descriptive representation. They don't give us understanding and comprehension in the sense I'm gesturing at. And I think this comes out very clearly in the fact that for essentially every physical theory we have, in fact, I'll leave out the essentially. For every physical theory we have, Navier-Stokes, Newtonian gravitational theory, general relativity, quantum field theory, you name it, I claim we have extraordinarily limited detailed knowledge of the structure of generic solutions of the field equations, of the equations of motion. Usually we know exact solutions only under conditions of perfect or near perfect symmetry or some other unrealistic assumption, two bodies, no external perturbative influences. And then we argue that we can apply such solutions to real physical systems because the approximation is adequate under appropriately controlled circumstances. That is to say, we have no real idea at all, in a representational sense, what the world would be like if the theory were true or largely true of it, for any physical theory. This becomes critically clear when one really stops to really think hard about the mind-blowing complexity and richness of texture of real physical systems in the world. Consider this, not glass, but cup of water. The little eddies and whirls of fluid motion that we can't see but are there because of minuscule temperature and pressure gradients, suspended particulate matter, dust and other schmutz, air bubbles affixed to the side, well, in this case of cardboard, not glass, but again, because of the impurities and inhomogeneities in the cardboard, the adsorption and evaporation of molecules into and out of air, hyperdense, stereometrically complex network of hydrogen bonds with extraordinarily rich symmetry patterns, as the weft of instances of dozens of species of ionic combinations of hydrogen and oxygen, H2O being, in fact, not even a majority of that, only a plurality. The staggering variation in structure of the electromagnetic field at every point of the fluid, the different radio channels, the same antenna playing Berg's Lulu and the BBC News, all the signals from all the mobile phones all over the planet, the gamma ray bursts from distant astronomical cataclysms, and on and on and on. And yet, our naively, ludicrously simple models work. They really, really work. Navier-Stokes theory gives an extraordinarily good model of the fluid, of the water in this cup, under an extraordinarily wide range of states of the fluid and environmental conditions. Not after I swallow it and it goes into the highly buffered digestive, highly enzymatic, buffered and enzymatic environment of my stomach, however. That's actually important. I think we forget in philosophy, we lose sight of how complex real physical systems are, and what a miracle it is there are almost naively simple-minded theories can still capture them. And correlatively, we forget how much distance there is between those very pristine models, those very, very, very few pristine models we actually do know in any given theory, and the real physical systems they purport to represent. And so we forget how many of those models would almost certainly do the representational task required, if any one of them does at all. How many of those models that we have no idea of how to construct in any way graspable by the human mind, or indeed we wouldn't even know how to identify one if it came up and bit us in the ass, because we just don't know what a generic solution to any of these physical systems, any of these physical theories look like. In the end, therefore, it seems to me, the idea of the standard view that the theory is characterized by the formalism and something like the sense of the family of solutions to its dynamical equations, Tarski models, possible worlds, what have you. It seems to me, if you really want to champion the standard view, it seems like you really have only two options here. We stipulate by fiat that there are a family of actual, or perhaps, depending on your modal predilections, possible in some sense, physical systems, though we cannot actually pick them out in practice, that are the ones represented by the solutions, and those are the models of the theory. Those are the, that's the empirical, that's an essential part of the epistemic content of the theory. Or we stipulate that the solutions themselves, for instance, vector fields on phase space, are the models, though we cannot represent them in anything like closed form. And again, just the overwhelming, non-denumerably many number of solutions we just wouldn't even. You just give me a vector field on phase space for some. That's the space of states of some physical system for some fixed physical theory. In general, I'm going to have no idea whether that actually represents a solution of the equations of motion or not. It's just too hard of a problem. In both cases, though, whichever of those two options you take, we are saying that the overwhelming majority of the content of the theory is something that we do not know, are in fact nowhere near knowing, and have good reason to think we will never know in anything remotely resembling thoroughness and detail. Nonetheless, the story goes, there's this mystical relation of subsistence between the formalism and the models that univocally and unambiguously fixes them. And that in turn gives rise to a magical relation of reference that just zaps out from the formalism of the world and latches onto the salient physical systems in a physically significant way. And we, in our supernal cognitive puissance, just know this. We are talking here, I think, of a Fichtean faculty of pure intellectual intuition that grasps without cognitive or perceptual mediation the Kantian Ding an sich, or I would say more precisely, we are talking of nothing at all. A semantic relation that is not known and cannot be known by humans in our actual current epistemic circumstances has no possible use in actual science and has no possible bearing on a fruitful and illuminating analysis of scientific knowledge. My rhetoric may make it sound as though only the realists are subject to my wrath, and I'm too tough. You can't. I'm actually. I'm burning with rage on the inside. probably appear somewhat calm on the outside. But that is not so. I intend my wrath to be shared among all philosophers, beholden in any way to something like the standard view, whether of a realist or an anti-realist bent. I mean, what is this fairyland of formal models through semantic tools the instrumentalist uses to make his predictions? And so I think this is something that Curiel thought about this morning, that for the instrumentalist, for the sophisticated instrumentalist, the semantics is just one more theory that he or she can call upon and make use of. But what is this theory of semantics? What is this tool? This tool does nothing in real physics. This tool provides us no real understanding of how real physics actually hooks up to the real world. All those who view it as something like the standard view, no matter how they think of the character of the relation between a theory and the world, have the same problem, whether you're a realist or instrumentalist or anti-realist or, I don't know, whatever you are. But what is the family of formal structures that characterizes the theory? Because that is what the standard view says. It's formal structure that characterizes the theory, and the physical content of the theory comes from the interpretive principles that we affix to the formalism. That is to say, which formal structures of the theory are even such as to be appropriate to serve as adequate representations of parts of the world? And how can we know this, given our woeful lack of actual knowledge about the details of the formal structure, the fact that we know so few actual solutions to the equations of any physical theory? What is the theory on this picture? I claim, following Howard's suggestion from the quote that I gave at the beginning of the talk, in order to address this problem, we need a mechanism or device for bringing a mathematically characterizable situation in the world of experience into substantively physically significant content with the mathematical structures of our theories, an intermediary that identifies the junctions where meaningful connections can be made between the two and embodies the possibility of the epistemic warrant we think we derive from such contact and connection, especially when we have access only to the most minimal, pristine, and physically unrealistic of solutions to the theory's equations. I claim that the schematic representation of the observer, in my very minimal pared down sense, in models of actual experiments play that role. Because what we so often do, since we don't have these exact solutions, or since we know so few exact solutions, and we need to model these incredibly complex systems, we know there are a million approximations and idealizations going on. We need some way to figure out which parts of our highly idealized and highly approximative, depending on which way you're working, models actually hooks up to which parts of the incredibly complex system that is the water in the cup. We need to know why the P in the Navier-Stokes equations represents pressure and the alpha represents shear viscosity, and in what way they do, given how incredibly complex, as you get to finer and finer scales, what the pressure of the fluid actually looks like. And the fact that shear viscosity isn't really a constant, but varies with temperature and pressure and all that, but it's useful for our purposes, and Navier-Stokes is treated as a constant. Given all of that just mess that lies between the beautiful, pristine Navier-Stokes equations, they're very beautiful, and the incredible difficulty of doing things like measuring the shear viscosity of a fluid in practice. How do we say that this very, very complicated empirical experimental procedure of measuring shear viscosity is pointing at the alpha, or the alpha is pointing at that? It's because we know, at least in principle, how to model the actual experiments we use and relate those models of experiments systematically to the terms that appear in the Navier-Stokes equations, and relate them to the kinds of the actual solutions we do know of the Navier-Stokes equations. So I'm going to now give a start. Well, I'm going to start a Stein quote and finish it on the next slide. In actual fact, the experimental physics is treated separately as a discipline in its own right. It is partly an art, an affair of both knowledge and manipulative and perceptual skill. But the possibility of connecting this art with a theory is closely connected with a certain possibility within the mathematical structure that is the theoretical framework, using the word I've introduced earlier, the possibility of representing experiments and of representing the observer schematically. I want to speak of schematizing the observer within the theory. The intention is to secure empirical content within experience for an abstract structure. So far as the fundamental theory is concerned, or rather so far as mathematically defined structures and rigorous arguments are demanded, schematic representation of observers, experiments, and observations is, I believe, as far as we know how to go. This leads, I'm now going to continue in the same vein, asking what is the family of physical systems that a physical theory treats, and how do we know what that family of systems is? And how do we know which parts of the theory, which actual solutions to equations of motion are viable as adequate and appropriate representations for the actual physical systems? The standard view gets right the fact that the family of systems that theory adequately and appropriately treats is a central component of the epistemic content of a theory. To identify the family of systems, we need to demarcate the regime of applicability, which is the family of systems that actually is applicable to. To do that, we need to do things like fix error tolerances, acceptable levels of precision, and so on. To do that, we always must make use of non-rigorous mathematical techniques and heuristic arguments and approximative, the loose application of approximative and perturbative principles, all of which cannot be represented, much less accommodated within the standard view. To do that, indeed, we need real models of actual experimental techniques representing the actual tools we have at our disposal for performing such measurements. For a theory's regime of applicability, I claim, changed over time with advances in practical knowledge. But the actual or possible family of physical systems the theory can adequately and appropriately treat, in general, if it's a good theory, and people are studying the problem, in general, will get larger and larger over time as our experimental practice and our experimental technique is perfected and improves. It's redundant, but you know what I mean. If demarcating the regime of applicability were not dependent on practical knowledge of the kind that changes, the current reach of experimental technique that determines fixed levels of precision and accuracy and so on, then there would be a fixed number once and for all, say 3.14159265359 onwards, times, let's say, 10 to the minus 6 centimeters, at scales smaller than which Navier-Stokes theory breaks down. Because ex hypothesis, we're saying that the family of systems that Navier-Stokes applies to is fixed once and for all, and doesn't depend on this kind of practical knowledge we can gain only by experiment. But that is just false. Navier-Stokes theory breaks down at different places for different types of fluid under different conditions, and the increasing acuity and resolution of our measuring instruments in conjunction with our increasingly powerful control of experimental error, both practically and experimentally, and the increasing sophistication of the models we can construct of our measuring devices, and the fine details of their interactions with different Navier-Stokes fluids under different conditions, all of that mean that such numbers as 3.14159265359 times 10 to the minus 6 centimeters become ever smaller over time. They are not fixed sub specia eternitatis. The family of models of Navier-Stokes, I claim, is an incoherent idea insofar as one wants to say it represents the totality of physical systems the theory adequately and appropriately represents and treats. This is a simplification. One can allow, say, a fixed function of shear viscosity, bulk viscosity, thermoconductivity, pressure, shear stress, and so on, rather than just a single fixed number. But the point is the same. If you allow such sophistications, such a thing can still be determined only experimentally. The formalism of theory, the equations themselves can't tell you what the breakdown scale is. The breakdown scale is fixed experimentally, determined experimentally, and changes over time. Thus, neither is the family of physical systems the theory adequately and appropriately treats fixed sub specia eternitatis. I think this is right. Scientific theory is not a Platonic form. It does not immediately exist independently of our actual epistemic state. Thus, it is only by dint of the practical forms and aspects of scientific knowledge not captured by a theory's formal machinery that we can determine a theory's regime of applicability. Knowledge of that regime, however, embodies perhaps the most important part of the epistemic content of a theory. Without it, we have no warrants at all for trusting our use of the theory, for understanding it as a theory, of a particular class of physical systems, and for knowing which individual systems that seem to be of that kind in some intuitive sense, say Mercury from general gravitational theory, this water when I actually shake it enough so that it just really kind of deviates from hydrodynamic equilibrium, Navier-Stokes can't handle that, are yet not adequately and appropriately treated by the theory for some purposes, depending on what your error tolerances are and what levels of precision and accuracy you demand in your measurements. There is also the contrary problem. To know what solutions and models of a theory's equations take seriously. The great relativist J.L. Singh remarks, it needs a lot of intuitive physical sense to know when to expect actual things to behave like the idealized models we make of them. To determine which solutions and models of a theory's equations represent in an adequate and appropriate way real physical systems, and which parts of those solutions and models that do represent real physical systems represent real parts of them. This is not the kind of problem that JB was talking about what counts as a physically reasonable space-time. And this is not the problem of gauge either. Consider again Navier-Stokes. It's a continuum theory. The solutions to its equations allow one to make, indeed they necessarily encode, physical predictions at arbitrarily small spatial and temporal scales, but we know that's not appropriate, but we know they're not appropriate for that task. It's, molecular effects take over when you reach certain scales. But we know we can safely ignore those predictions of the theory in assessing its adequacy and soundness. General relativity is scaleless. One can't distinguish a model of a Schwarzschild. If I just give you a Schwarzschild metric, you can't say whether that represents a Schwarzschild black hole of radius 10 to the minus 10 to the 39,876 centimeters from one of radius 88 million kilometers like we think Sagittarius A is. And yet we also know that the theory is almost certainly appropriate only for treating the latter, not for treating this probably incoherent, actually, spatial interval. But nothing in theory's formalism can tell us that without the input of knowledge that can be had only by experimentation that delimits the actual applicable and adequate scope of general relativity. So I only have, I think, 5 minutes left.
I think we started late, a little bit late.
That's fine. So I think I'll need like 7 or 8 minutes.
Great.
So I think I can get maybe 2 or 3 minutes late. So the standard view has, I think, another related shortcoming, that according to it, all scientific knowledge is essentially of one undifferentiated kind. True, or at least epistemically justified propositions about states of the world and perhaps about the global or gnomic structure of the world, independent of the state the world is actually in, which may, e.g., be used to try to represent modal structures such as is captured by subjective conditionals. And this comes out most clearly again in the picture of a theory semantics that naturally accompanies the standard view of theories that are just fixed by a determinate and pristine ontology. Again, this is not an accurate picture of scientific knowledge. Scientific knowledge has many forms and aspects that cannot be well captured with a simple picture. The structure of the knowledge that characterizes a theory as a physical theory of the types of physical systems it purports to treat must include all forms and aspects of knowledge the theory has endowed on us. If, as I've been arguing, we want to do things like actually demarcate the set of physical systems the theory actually adequately and appropriately treats. Semantics that captures only knowledge, epistemic content that is impossible in principle for humans to know, is useless as a semantics on which to ground an analysis of the nature of scientific knowledge and its epistemic warrant. I take that to be the gist of the paraphrase I gave earlier of Bill Demopoulos' remark. But if the semantics does not do this, however, then what does it do, and why should we care about it? So a useful classification of what I've been calling the theoretical and the practical forms of scientific knowledge is suggested by the following observation of Stein from his some reflections. It is hard but possible to learn theory by self-study from books. It is surely much harder to learn experimental techniques with a teacher to help one acquire skills. But what I suspect to be impossible is to learn the principles of experiment without actual experience with the relevant instruments. How one is able to learn different parts of the epistemic content of a theory may seem at first glance irrelevant for analysis of the character of the knowledge to be learned. To the contrary, I think Stein has put his finger on something very deep about epistemic content here. How it is possible to come to learn something fundamentally shapes and constrains the kinds of epistemic warrant we can have for it, and how we may bring it to bear in possible evidential relationships to other pieces of potential knowledge. Theoretical knowledge of the sort Stein describes here in the first part of the quote has the peculiar and remarkable property of being representable by a well-arranged sequence of propositions, a well-arranged textbook, a well-written textbook. If it did not have that property, we could not learn it from such a sequence, but we do, although it's difficult, but we do. practical knowledge cannot be effectively represented in that way. There's a wonderful anecdote about this, but about the kinds of knowledge one can gain in experimental practice only by use and acclimatization, so to speak, of practice with the actual experiment with the instruments. But for lack of time, I'll
Take the view.
well, okay. So during the running of the Event Horizon Telescope, which is in a sense which is an array of eight linked observatories in the 1.4 millimeter range around the world that are being linked as a very large baseline interferometry apparatus to try and take a more or less direct image, first one, of a black hole, Sagittarius A at the center of the galaxy. I witnessed the following exchange between Shep, who is the head of the EHT team, designed it, runs it, drove it, and an instrumentalist at the Chilean Observatory, which is 3,000 meters above sea level, that's relevant, who was having trouble with one of the specially designed instruments. So a crystal transistor was malfunctioning. And in this video conference, I was a fly on the wall just watching because it was so fascinating. Shep said, oh yeah, I've seen this before. Here's what you do. Take them down to 1,000 meters above sea level. Just leave them for a few hours. They'll settle down, and then when you take them back up, they'll work. And the Chilean instrumentalist said, why? Okay, fine, I'll do that, but why does that work? She said, I have no damn idea, but it does. And I think that this is not meant to inspire skepticism about the results of the EHT. Shep knows what he's doing. This is part of the practical knowledge associated with observational relativistic astronomy that I doubt anyone will ever find written in any book. Moreover, I mean, of course, even if it is written, it's the sort of thing one could not learn from just having read the book. Of course, one could learn that particular trick, but to learn how to play with the instruments was to be able to acquire the feel for them necessary to figure out such tricks for solving problems. That is something that cannot be learned from a book, I think, as Stein emphasized so beautifully in the passage I quoted. I think this lesson generalizes how it is possible to learn different pieces or areas of scientific knowledge as one very important criterion for determining the kind of knowledge one is dealing with, how it can be represented among other things, and thus whether it can, e.g., be captured by formalism and coordinating principles or representational capacities. The practical form of knowledge of the art of experimentation, inextricable from the epistemic content of the theory one considers, cannot be formalized or even just well captured in book form. Most theoretical forms of knowledge, I think, can. The latter is, to speak crudely, propositional in a way the former is not. That is not, however, so facto imply that it is more important for a proper understanding and analysis of the character and content of the sum of knowledge that the theory embodies, that characterizes it as a physical theory of that sort of family of physical systems, and yet it is systematically and invariably completely ignored in almost all serious philosophical analysis of scientific knowledge and the structure of theories. Beautiful long quote from Grouch, G.R. from A to B, about theories, but I'll skip it to get on. I think we get misled in philosophy by a picture. We fixate, I think, on how we were taught the physics, but we forget how we learned it, and most of all, how we actually know that we are warranted in believing that it is to be appropriately and adequately about some part of the physical world. And there's one final distinction I want to make about knowledge. This was alluded to, I think, by Chris in this talk. Again, following Howard, among different aspects of scientific knowledge. I'm construing, Howard says, the word knowledge in a wide and ambiguous sense. The reflections I'm proposing have as their object A, our knowledge in physics as an achieved result, knowledge as the knowledge we have of X. Our knowledge as susceptible of justification or defense, that is, as involving a structure of evidence for its asserted contents. And knowledge, science, as to appropriate a word of Isaac Levi's, an enterprise, an activity aimed at increasing our knowledge in sense A by means appropriate to the constraints of B. I would add this list of fourth, closely related to but distinct from science B, the one involving the structure of evidence. Knowledge as ground for epistemic warrant, for other knowledge claims, and for furthering the enterprise of science. Call this D. And not all knowledge in its aspect A can play this role. Smeek's description of the understanding of FLRW models in the 1930s, I think, is a very nice example of that. It gave us those models, the way those models were understood in the 30s, gave us some understanding about how the physical world was, but they certainly no one would have used them as epistemic warrant for further knowledge claims. So the standard view can't do this. In another sense, however, so I think I have 2 more slides left.
Go for it.
In another sense, however, the standard view gives too much as an answer to the question of the scope of a theory's epistemic content. For it says that every question one can pose to a theory has a determinate answer. And in a purely formal sense, this may be correct, but if one wants to know whether the answer given is relevant to the real world, whether the answer counts as scientific knowledge in the senses, for instance, of signs B and C and might D, then one has to know, among other things, the scope of the theory's regime of applicability, all the breakdown scales, and there are almost invariably many different breakdown scales associated with a given theory holding under different kinds of conditions. One has to know when it's a good theory, and for that one must have ref course knowledge that one can come by only by experimentation and the theoretical representation of such experimentation that includes schematic representation of the observer. And insofar as this essentially represents knowledge in Stein's aspect B, it can't be given as physical interpretive principles in any standard sense, one that includes knowledge cleanly separable from any knowledge represented purely by the theory's formalism. Our knowledge of where and how Navier-Stokes theory breaks down is in large part based on and justified by experimental results as represented in and put in immediate contact with the mathematical formalism. It's also deficient, I claim, with regard to knowledge of aspect A, insofar as it precludes fundamental understanding and comprehension gained of parts of the world that can be had only by heuristic and formal arguments that cannot be formalized. A good example is the way that the kinematical constraint of Navier-Stokes theory, that heat flux is always orthogonal to fluid flow, that's part of the mathematical formalism of the theory. If the heat flux of a fluid is not orthogonal to the fluid flow, you cannot in fact consistently solve the Navier-Stokes equations. That fact actually encodes, if you try to figure out what that means physically, it actually encodes the fact that Navier-Stokes theory is valid only for fluids quite close to hydrodynamical and turbodynamical equilibrium of a certain kind. But the arguments you have to use to extract that understanding cannot be formalized in any way representable on something like the standard view's pristine ontology. And like I say, the best arguments I know of for this are, strictly speaking, incorrect in part, incoherent as a whole, and even inconsistent in several ways with respect to the formalism of the theory. Nevertheless, they really give us this understanding of how Navier-Stokes represents these fluids and what it's saying about these fluids.
Go for it.
I'm just going to say 3 fundamental claims of the talk. That a theory is best characterized by its epistemic content, that the epistemic content consists of theoretical and practical components that are not cleanly separable, and that one cannot represent a theory as a theory about the world without knowing how in practice to be able to schematize the observer in theoretical models. All 3 of these for me are themselves not cleanly separable, but hang and fall together. You accept one, you accept all 3. One for all and all for one. The 3 musketeers of claims about scientific theory. Last slide. The miracle of science is that theory and experiment are consonant with each other. The necessity of science is that they are inextricably so, not, however, as equals. Theory plays Boswell to the subtle and tragic clown of experiments Johnson. Thank you.